Today we're going to talk about graphing some functions that we might not be otherwise able to graph unless we knew a little bit about calculus, first and second derivatives. So I'm calling this lesson Putting It All Together in a Graph. What I'd like you to do, or what we're going to go through today, is we're going to graph a function. Let's say it's f of x is equal to x cubed minus 3x squared plus 4. So normally we wouldn't be able to graph very much of this unless we set up an XY table and plugged in several numbers. But since we know some things about calculus and first and second derivatives, concavity and increasing and decreasing and local extremas, we're going to put all that together in this one graph of, of this function. And I'd like you to do some things, or I would like you to indicate some things on this graph, like the x and y intercepts, extrema, the behavior, whoops, this is end behavior I'm talking about, but end behavior is the same thing as, whoops, not x, as x approaches positive and negative infinity. So what is this happening? What's happening to this at the end? You probably remember pretty well what happens to a cubic function on both sides of it, but we'll talk about that. And then I want you to indicate the concavity. Oops. Ugh. And the inflection points. So we'll put all that together in this graph, and I think I'll try to be a little bit neater in my graph. So let's draw some nice x and y axes on here. And let's go out to 4 and back to -4 and up to 4 and down to -4. And if we need to add more tick marks, we will. So first of all, the x and y intercepts. I guess we'll call this A, B, C, and D. So the x and y intercepts, first of all, the y-intercept is when x equals 0. So f of 0 is usually pretty easy to find. F of 0 is equal to 0 minus 0 plus 4, which is 4. So there's one point on our graph, 0, 4. So that's right up here at the top. There's a y-intercept. Now the x-intercept is when y equals 0. So if you set x cubed minus 3x squared plus 4 equal to 0, you don't know how to factor that. There's really no method, except way back in the fall we talked about the rational zero test to see where the zeros are, which are the x-intercepts. So what we're going to use is the rational zero test on this to figure out where this crosses over the x-axis. So this is the y-intercept. The x-intercept, use the rational zero test to see possible zeros. The rational zero test, if you remember that, it is the factors of the last term divided by the factors of the leading coefficient. So the possible rational zeros here are plus and minus 1, plus and minus 2, and plus and minus 4. Those are the possible zeros. Well, how do we tell which ones are for sure? What we're going to have to do is do some synthetic division to see where we get a remainder of 0. All right, so let's set up a Let's set up a synthetic division on this particular problem. So we have a 1, -3. It's a 0x, so don't forget the placeholder of 0. So here's my x cubed term, here's my x squared term, here's my x term, and here's my constant term. And let's try +1. Let's see if we get a remainder of 0 here. So drop down the 1. 1 times 1 is 1. Add, and you get -2. Add, and you get -2. And you get a remainder of 2. So, nope. Now let's try x equals 2. This is just a try. Let's try x equals 2. So we have again 1, -3, 0, and 4. So drop down the 1. 2 times 1 is 2. Add them up. -2, add them up, and -4, and you get yes. So x equals 2 is one of the zeros, and what we have remaining is this x squared minus x minus 2 polynomial. So if we wanted to drop this down as a factor, we can say f of x is equal to x minus 2, because 2 is one of the zeros of this, and what remains is x squared minus 1x minus 2. And now you can see that this quadratic is factorable because there are factors of -2 that add up to -1. So we can call this x minus 2, and then factor this out, and you get x minus 2 times x plus 1. And if you set that equal to 0, you find the zeros of this function. +2, and this is a repeated root. I'm not going to write it again. And -1. So these zeros, those are the x-intercepts. So let's draw those in. X equals 2 and x equals -1. So we've got the x and y intercept, letter A. Now to get the extrema, you're going to just find the derivative and set it equal to 0. So this is part B, extrema. F prime of x is equal to 3x squared minus 6x. Set it equal to 0, and you can factor 3x out of there. So x is equal to 0 and x is equal to 2. Those are possible. Extrema. And you can do two methods. You can either use a first derivative test, or you can use a second derivative test to figure out whether these are maxes or mins. And I think I'm going to use a second derivative test. So I'm going to find f double prime of x, the second derivative, go up to the first derivative, and 3 times 2 is 6x minus 6. So now I'm going to just plug in x equals 0 and find f double prime of 0, because that's my critical value here. F double prime of 0 would be -6. So what this means is it's concave down. Concave down is a graph that looks like this. So this would be a max. X equals 0 is a max. And now I'm going to do the second derivative test on my other critical value, which is 2. And the second derivative, f double prime of 2, is 6 times 2 is 12 minus 6 is positive 6. So since this is positive, it is concave up. Concave up looks like this, and that will give you a min down here at the bottom. So you have a minimum value at x equals 2. So there are our two extremas. So now we have a local max at x equals 0, and then if you go back up to the original problem, you've got to find f of 0 and f of 2 to find the max and min. So down here, the max, f of 0, and we've already done f of 0. F of 0 is equal to 4. So this point right here is also going to be a max. So let's label that as a max at 0, 4. And then our min we're going to have to find f of 2. Well, we've already found f of 2 because that is one of our x-intercepts. F of 2 is equal to 0. So this point right here will be a local min. Oh, let's write local. This right here will be a local min. So we found our two extremas. The next thing we're going to do is a behavior as x approaches infinity. So because this is a polynomial, it's a cubic and the leading coefficient is positive. This is going to fall left and rise right. So that means as x approaches positive infinity, f of x will also approach positive infinity. And when x approaches negative infinity, f of x is also going to approach negative infinity. So that's what it means to fall left and rise right, because x gets bigger and so does y, and when x gets more and more negative, y gets more and more negative. So there's your end behavior. And then concavity and inflection points. So we have the second derivative already worked out. If we set the second derivative equal to 0, 6x equals 6, so x equals 1 is the possible inflection point. And this is our letter D, finding the second derivative. And to figure out if it is actually an inflection point, you're going to set up a second derivative sign table with only x equals 1. So this is f double prime sign table. So when x is less than 1, when x is negative, you're going to have negative values here. So this would mean that it's going to be concave down for x values less than 1. And when you put in a number that's greater than 1, it's going to be positive. So this part here is concave down. This part is concave up. So x equals 1 is an inflection point. So now we just have to find f of 1 to figure out the y value. So f of 1 is 1 minus 3 plus 4, which is 2. So we have 1 comma 2 right here, and let's label that as our inflection point of 1 comma 2. And our local min was at 2 comma 0. So now we have everything we need. We have all the concavity, we have the one inflection point, local max and local min, and we know what's happening and behavior-wise. So starting here, we need to draw the graph concave down. And our end behavior goes to 0. And then starting here, we need to draw the graph concave up. And it's a local min, so it comes in and it goes up like that. So there's a rough sketch of that graph. Now the other thing I want you to do is we're going to draw the first and second derivatives on this graph right over the top of it. And I'm going to draw it in 2 different colors. I'm going to draw the first derivative in red and the second derivative in greens, just so you can get a look at what the derivatives look like on top of the original graph. So let's label this f of x. All right, so up in the instructions here, it says graph f of x, and I want you to graph f prime of x and f double prime of x right on top of it. Well, we already know what f prime of x, the equation is, and what f double prime is, what the equation is, so we can actually figure that out and draw it appropriately. But one thing that we have to make sure that we know is when we have our f of x graph and we want to draw the derivative, anytime you have a local max or a local min, you have to have an x-intercept. And I think we've talked about this enough times. So here's our local max, our first derivative. So I'm going to draw the first derivative in red. It's got to have an x-intercept here, and it's also got to have an x-intercept right there. So this is going to cross over each other. to the left, or when x is negative, this slope is positive. It's very positive here, and it becomes more and more and more gradual. So this graph is actually going to come down like this. It's going to hit this part right here. Now we have, from here to here, we have a negative slope, so this derivative graph has to be underneath the x-axis. And where the inflection point happens, that's where we're going to have a local min of our derivative graph. So here's our inflection point. Right underneath there is a local min. And it comes around, and we've got to come through here. And now our graph becomes, it has a positive slope. So we're going to go like this. So this right here in red is f prime of x. And then the last thing we're going to do is draw in the derivative of the derivative. Well, the derivative of the red, I'm going to draw the second derivative in green. This has a local min right here. It's actually an absolute min also, so we're going to have an x-intercept right above that local min. So 1, 0 is an important part of the second derivative graph. And this graph, we already know the equation. It's 6x minus 6, so it's pretty steep. But looking at the concavity, this part is concave down. So the concavity means that we're going to be underneath the x-axis, like this. And then this part of the graph, of the original graph, is concave up, or in other words, this part of the graph has a positive slope, this part has a negative slope. So now we're going to have our second derivative graph, f double prime of x. And hopefully this makes sense because we have a cubic original, we have a quadratic first derivative, and we have a linear second derivative. So that's kind of putting it all together with all of the things that we've learned about in the calculus part, and some old stuff with the synthetic division. And I think that'll probably be it for today. We'll get some practice at this tomorrow. Have a great night.